Hello everybody and welcome back. This time we're up to question number 9 on our 2011 Euclid paper, so let's take a look, shall we? Alright, so it's a written one, obviously. Let the floor function of x, that's what this one here is typically called, denote the greatest integer less than or equal to x. For example, the floor of 3.1 is just 3, the floor of negative 1.4 is negative 2. So it doesn't take the integer part. It rounds down until you hit an integer. And for example, if we're already at an integer, it just stays the way it is. Okay. So it's a pretty common function if you haven't seen it before. Anyways, what are we going to be doing with the floor function? Suppose that f of n is 2n minus, then we've got the floor of 1 plus square root 8n minus 7 all over 2. And okay, and gn is 2n plus. So that's really the main difference here, because it looks like we still have a plus sign in here. 1 plus square root 8n minus 7 over 2 for each positive integer n. Okay, and then we've got 3 questions, but immediately what I'm thinking is 2 things. One, the expression inside the floor looks a lot like a quadratic formula, negative b plus or minus square root. So we might be able to sort of unravel and get a quadratic in terms of n that might be relevant to our fn's, our gn's, and what we're being asked for in the question. The second thought I had, which was actually the first thought I had, but I'm trying to present them in a nice order. The second thought I had is just because I've done so many of these contests, and you have too if you've been doing a lot of practice. This is shockingly close to, if not exactly, this 1 plus square root 8n minus 7. The 8n minus 7 is sort of triggering me to remembering, I think this is in some way related to triangular numbers. I think, so triangular numbers are numbers of the form, they've got an n used, so k times k plus 1 all over 2. So they're sums of natural numbers, so 1, 3, 6, 10, 15, these are triangular numbers. But if somebody hands you a triangular number, like 15, and they want to know, okay, what number do you plug into that k times k plus 1 over 2 formula to get 15? You have to set up a quadratic, and I'm pretty sure the quadratic you get is very, very close to that. The reason I presented, even though this was my first thought and I presented it second, is because if this does turn out to be triangular numbers, I didn't want it to seem immediately like, aha, he must have looked up solutions. I don't look up solutions when I do this. I've just done a lot of math contests. And it could be that this has nothing to do with triangular numbers, but that is the immediate thought that jumped into my head. And if you do enough of these contests, that might be a thought that jumps into your head too. We'll see if it pans out. I haven't actually read the rest of the question. But definitely this is looking like it's a quadratic formula for some quadratic, where n is probably a constant term. So we're going to keep our eyes on that. Okay, A, B, and C, we can read them one at a time, I guess. A, just determine the value G 2011. Just plug in the year of the contest in. They just want to make sure, do you understand how to work with this? So I've got my calculator handy. Let's plug it in. 2011, so it'd be 2 times 2011. And then G is the minus one, right? No, G is the plus. So plus floor 1 plus square root 8 times 2011 minus 7 all over 2. So I'm just going to double check that again just before I start calculating. Yep, okay, we're good. All right, so 4,022 plus, we got floor of 1 plus, this will all be over 2, square root of, all right, see, 8 times 2011 minus 7 is 16081. And does that have a nice square root? Let's find out together. It does not. That's okay. So I'll just say 1 plus 126.8-ish. We don't have to be super precise because we're going to be rounding down in a moment anyway. So add 1, divide by 2. 4022 plus the floor of 63.905, I guess, if you want. But that would just be 4022 plus 63, because remember the floor rounds down until you hit an integer. So 4022 plus 63 is going to be 4085. So we probably bagged ourselves 1, maybe 2 marks there. Nice little A part. But this is often what happens on questions 9 or more commonly question 10. They'll introduce a brand new concept, in this case, some brand new functions. And, the A part is just 2 quick marks. Can you plug in? Can you do a simple calculation? Can you find the next 3 terms of this sequence? And you should always try them, even if you have no idea what's going on for B, C, or D. Always try them, because it's a couple spare marks, and that's fantastic. Okay, so getting back to it, we want to read B part. Determine a value of n for which f at n is 100. Okay, so the a value suggests that there might be more than one way to get 100 here. But what are we going to do? It's kind of hard to undo equations that have this floor function here, but I'll see what I can do. So I know 100 is fn, and that's 2n minus this 1 plus the 8n minus 7, square rooted all over 2. Okay. Now we got to show our work, so I don't just want to guess and check my way to something and say, aha, I did it with guess and check. But it might not be a bad idea to try some things like, 2n, n's got to at least be 50. And then you're hoping that the floor expression would then be 0, because we need 2n to be 100, or to be more than 100. So we could definitely say, well, definitely n is bigger than 50. So we might try something like 51, for example. 2 times 51, 102, but it's more important that we say 8 times 51 is 408 minus 7. And square rooting that's about 20. 20 plus 1 divided by 2 is about 11. So we're not quite there, but we're sort of in the ballpark, I guess, is what I'm trying to say. So I would guess maybe something like 60 might. Actually. What do we want to do here? Well, this expression over here, n's got to be greater than 50. Greater than or equal to 50. Since these sorts of expressions are always, well, they're definitely non-negative, so we could certainly say this is greater than 50. Although it could be rounded down. Anyway, okay, now what I want to do is I want to sort of talk about this expression here. I want to say something like, well, it's about 20 for some of these things. I really don't know a better way to do this other than guess and check. I was hoping to find one. I suppose what I could do is I could try and follow up on my initial thought of this looks like a quadratic, or my better thought, which was this looks a lot like the quadratic expression you get when you talk about triangular numbers. And that might give me some idea as to what to plug into f at n to get 100 back out. I mean, it might be something which I don't quite know what we would want in terms of triangular numbers. It's interesting. Okay, well, okay, so and you don't want to spend too much time doing this, hemming and hawing between two methods. I can either just start guessing and checking. I definitely think it's something at least greater than 60 should do the trick. Maybe around 70? I don't know. Or I could stop and try and develop a little bit of theory. If I'm going to develop some theory, try and explore the Fn and the Gn in a much more important sense, then I'm probably going to want to take a look at C part to give me a little bit of a guide, a little bit of push into the sort of stuff that I might want to be looking at. I think I'm just going to do some guess and check. And then when I work out my answer, I can write it up nice and neat by saying, we claim n equals 70 works. I don't think it will actually be 70, but if it is, okay. But, we claim n equals 70 works. Here are my calculations, okay? I don't think they worded the question where that wouldn't be allowed. They just said determine a value. So what I'm going to do is I'm just going to try some values. So I'm going to try n equals 70. The reason I'm skipping over, so when n was 50, actually when it was 51, this expression here was about 11. So I actually, maybe 60 might work. Let's try 60. So f of 60 would be 120 minus 60 times 8 minus 7. The minus 7 really doesn't do a whole lot. So that's about 21 plus 1, 22 divided by 2. So subtract 11.3, but you round it down to 11. So it'll be 109. So it's actually 60 is too big. I don't know, try 55. Basically, I'm doing a computer search. I know 50 won't work because I already did that one. 60 is too high. Let's try halfway between the two. So that would be 110 minus, again, about 11. That's kind of interesting. We might talk about the range of values we get in here. Like what produces this being 11? So if that's the case and we want 100, maybe we should try something that gives me 112. No, we'll try the 110. I don't know exactly when it's going to switch over, but so 55 times 8 minus 7 square root of 433, 20.8 plus 1 divide by 2, 10.9, and there we go. So 110 minus 10, because 10.9 rounds down, and we get exactly 100. Now, they said all values, but they didn't say all values, but they said a value. So now I'm kind of curious, would 56 give us 100 as well? So that doubling that would be 112 minus, and then 56 times 8 minus 7, 441. So its square root is exactly 21. Interesting. 21 plus 1 divided by 2 is 11. And that's actually 101. So that's just a little bit more. 54 shouldn't. 54 should be 108 minus 10, which should be 98. Okay, so there is really just the one value, f of 55. How might we go about doing that? Why 55 giving us 100? Interesting. Very interesting. And I'm also starting to think, just because I was talking about triangular numbers a little while ago, 60 is halfway between 55, which is the 10th. Sorry, it's not halfway between, but it's between 55, which is the 10th triangular number, and 66, the 11th triangular number. And look at that, we got 11 here. 55 is the last of the is the 10th triangular number. After that, so it looks like, I think this expression here is going to round up to the next triangular number and figure out and return to me which triangular number that is. I think that's what's going on here. And we could actually explore that a little bit and put that in closer to explaining why F55. But I honestly think you'd get the marks if you said something like, we claim and it equals 55, will do. And then you just show your calculations. I think that would be perfectly fine. I didn't mark this year, so I don't know exactly what the marking scheme was, But as long as you explain the 10, explain the 110, I think that'd be fine. I think it'd be fine. I think the bulk of your marks are more going to be earned with C part, whatever C part ends up being. Okay, so what have we got for C? Suppose that A, so we got a set here, F1, F2, F3, and B is G1, G2, G3, and so on. So A is just the range of F, B is the range of G. So all values you could get out by putting positive integers in. Prove that every positive integer M is an element of exactly one of A or B. So there's no way to make M equal to Fn and f of some n and g of some k. It doesn't have to be the same n. Interesting. Okay. So there might be sort of two approaches to this C part. We might have to show that, like, one way to do it might be to be able to say, all right, exactly these numbers here will be the outputs of an Fn. Exactly these numbers over here are outputs of a Gn, and you can see clearly by the way I've described these, like all even numbers come from the Fn's, all odd numbers come from Gn's. If you said something, if you were able to show something like that, then obviously only one number can, every number M is either even or odd, so will only belong to one set. That's the idea. So if I can describe everything that Fn is and describe everything the Gn's are, and show that that makes up all the positive integers and that there's no overlap, then that would be fantastic. Another thing we could try to do would be proof by contradiction. We could say something like, well, suppose there were a k and an n, so that f of k is equal to this m, and g of n is also equal to this m. That this m is in both a and b, and we can show that that leads to some nonsense. Okay, that's another option that we might try. Now, because I saw that quadratic stuff, because I'm starting to try and guess as to what might be going on with triangular numbers, I think what I'm going to try and do is try and investigate Fn, Gn, and be able to say, well, exactly these numbers will be the Fn's, and exactly these numbers will come from Gn's, and clearly there's no overlap. Clearly it's all positive integers. Okay, so I think that's the approach I'm going to take. Now, if that fizzles out in 10, 15 minutes, I might go to a different question if I were actually writing it, because you want to keep your mind fresh. You don't want to get stuck on the same question for half an hour. But unless there's nothing else to do. But I also might try my other method, try the proof by contradiction, or I might try and come up with something else. But I want to explore the Fn's a little bit. Now, I don't know exactly what it might look like, but I really am looking at these triangular numbers here. So I'm going to go with my instinct here that I wrote over here. So here's what I'm going to say. I'm going to say something like, I claim Fn, I claim, what I want to talk about is the hard part to understanding F and G is that floor expression. So I claim that if n is less than or equal to the teeth triangular number, and I'll just write the expression t times t plus 1 all over 2, in case whoever's marking is not familiar with triangular numbers, is less than or equal to the teeth triangular number, but greater than the t minus first triangular number, then 1 plus square root 8n minus 7 all over 2 is t. That's based on what I sort of observed here fiddling around with these numbers. So I definitely right now believe this to be true. I'm making the claim. I'm going to see where this goes. If it turns out in 3 or 4 minutes I can't find a way to make this true, or I find examples where this doesn't work, I'm going to have an issue. Also, something I just thought of doing, I might want to work out F1, F2, F3, G1, G2, G3, work out a few of these to see if I can notice anything. But I'm hung up on these triangular numbers. Also, I'm not exactly satisfied with the way I answered B, so I'd like to be able to understand F of n a little bit better. All right, so how would this work? So I need to prove it. So the t minus first triangular number looks like this. And I know that's less than n. And n is less than or equal to t times t plus 1 all over 2. Now if I do 8 times this, we'll get 4t t minus 1 less than 8n less than or equal to 4t t plus 1. We're going to have to start doing some interesting stuff. 4t squared minus 4t. We'll do minus 7. 4t squared plus 4t minus 7. And now these aren't nice functions that I can square root. So I'm unhappy with this. I have the right expression. But I can't square root this. Because the thing that really sort of wowed me from them there is when I did 55, 8 times 55, the 10th triangular number. Oh no, 56. When I did 56 times 8 and subtracted 7, I did get something that was worth mentioning. So let's instead do it this way. N's an integer, so I can absolutely do this just adding the 1 to both sides. So if I add 8 here, and I add an 8 here, and then coming along subtracting 7, I get plus 1s. There we go. That's nice. Okay, I thought it was 55 that gave me the exact answer. It was 56. And now I realize, this is 2t minus 1 squared. Oops, I've got to change my signs as well. And this over here is 2t plus 1 squared. So now if I square root, we'll take the positive square root. We get that. Add 1 to both sides. So we get 2t less than or equal to 1 plus 8n minus 7 less than 2t plus 2. And divide by 2, we will get t less than or equal to 1 plus the square root of 8n minus 7 all over 2 less than t plus 1. And so when I floor it, you don't have to know the name of the floor function. You can just say when we use this function, this expression. I don't think they gave it a name, did they? No, they didn't give it a name. It's called the floor function if you're curious. Like floor, like what you walk on. So when we use floor, we can see we round down to the nearest integer, and that'll have to be t, because the next thing is t plus 1, and we know my expression is less than t. And this is t as desired. Okay. One thing you might want to do, clean this up by saying, okay, so This is the n that I have described, but since n is an integer, this means the same as the expression we have over here. This wouldn't be true, like these two expressions are not equivalent unless you're talking about integers, so that might be a good thing to add in. But okay, so now I know just sort of round up to the nearest, sort of like almost like a triangular number ceiling function, which is kind of cool. But sort of round up to the nearest triangular number, and there you go. And that would make b a lot easier. Because then you could say, well, I know I need to get 100, so we're definitely looking at something bigger than 50. What are the next few triangular numbers? Well, 55. And you say, okay, so 51, 52, 53, 54, 55 will have this floor function give you back 10. And that works for 55. 66 would be the next one you'd get for 56, 57, 58, 59, and so on. You'd get 11, and that's the ends are now too big, so that might be a very nice way to write up b. Just a thought. But I've moved on to c at this point. But yeah, knowing this would make writing up b a lot easier, a lot nicer. I'm not happy with my guess and check that I sort of did. But I was happy with the experimentation because it led me to sort of realize this triangular number thing, which I sort of suspected when I first saw the expression, as I mentioned to you guys. Okay, but how does this help me with C? Does it help me with C? That is a fantastic question. So, definitely true, but maybe we should start looking at F1s and F2s and so on. So F1, but now this is going to be a lot easier. I won't have to grab my calculator or anything. I can just say, well, the one is the next triangular number up from 1 would just be 1. So I'll have 2 times 1 minus 1. F of 1 is 1. F of 2, the next triangular number is 3, and that's the second triangular number. So I'll have 2 times 2 minus 2, and that'll be 2. F of 3, however, is going to be 2 times 3. It's still the second triangular number, so we get 4, not 3. F of 4, F of 5, F of 6, we'll even do F of 7. But these three, the nearest triangular number that's greater than or equal to them is 6, so we'll be subtracting by 3 for all of these. Okay, very easy to do, don't have to do any of that square root floor function stuff. So we'll get 8, 10, 12. And we might just, sort of test for any patterns here. 5, 7, 9. Kind of interesting that these are all odds. These two are evens, odds. So what I'm thinking is, just based on what we've got here, what I'm thinking is this. If the next greater than or equal to triangular number is an odd triangular number, so an odd position triangular number, so like the first, the third, the fifth, F is going to give you all the odd numbers between starting at 5 and going up to 9. But it looks like it gives you odd numbers, but for an even position triangular number being your next one, F's going to be even, and I assume G will fill in the gaps and be odd there. That's just based on what we've got here, and knowing that what they're asking me to prove is going to have to be true. Now F of 7, we are back to, and we're here at 10. Notice these are going up by 1s when we switch. Very interesting. All right, now G at, we'll do G on the next page. I don't want to cram G off to the side just because I'm doing it second. G of 1, I assume, is going to be 3. But I can already fill in the floor function part to these. So this will be plus 1, this will be plus 2, this will be plus 2, plus 3, plus 3, plus 3, plus 4. And just doubling these numbers in here. So we get 3, we get 6, we get 8, we get 11, we get 13, we get 15, we get 18. Okay. So these definitely are different than the numbers we have over here. The G's are also, I mean, they start off a little bit bigger. And so I certainly agree with their statement, which is good because we want to be in a position where we agree with it, but we also want to be able to agree and prove it. And that's where to go from here. So notice with G1 we got, so the switch over here came at F2. And then, so even, odd, I'm gonna color code some things. I'm also gonna try to not draw over my previous work. Maybe we can do that. There we go. Put odds in red. Okay. And so we got the only odd number with 1 there. Then we got even numbers. Then we got 3 odds. Then we got, I assume, 4 evens. And here we had odds as well. And then we had 2 evens. 3 odds. This isn't shocking to me that I'm getting 1, 2, 3 odds and evens. But what I'm trying to do is I'm trying to say, okay, this 6 and this 8 should fill in the gaps over here to take me between 5 and 9. Now, why 5 and 9? Why is it that stretch of numbers that we're working with? And the 3, G1 being 3, fills in the gap here. And the 11, 13, and 15 will fill in the gaps down here. But how do I know what range of numbers I should be talking about? So, I'm gonna try and write down what I think's going on in a claim, and then we'll see if we can prove it. So I claim for the claim for odd t that f some expression in the f's all the way up to f of t times t plus 1 over 2. And so there's the third triangular number, and that's the last one here. I claim that these are the the t odd numbers in the range. Now we start with 5. So this was 5. This would be 9. So it was t times t plus 1 all over 2 plus t. No, because you double your input number, so t times t plus 1 times 2 plus another t. There we go. Is there a nicer way to write this? Take out the factor of t times 2t plus 3. Oh, this should be a minus t. So t times 2t minus 1. That'd be 3 times... Not quite, because this expression needs to be 9. So minus 3? So I got 12. That's 2 times 3. Oh, minus 1? T minus 1? Oh no, the multiplying by 2 doesn't come into it there. So, oh, it's just t squared. And 9 is 3 squared. Okay, so. And it looks like, yeah, because there's 4 squared, there's 1 squared, there's 9. I bet the next one will be 16. And yeah, we've got 4 even numbers from 10 to 16, and the 11, 13, 15 fill in the gaps. It doesn't even look like this needs to be for odd t's. Oh, well, same parity. And then this will be t minus 1 squared plus 1. We start with 5, which would be 4 squared, or with 2 squared plus 1. And what expression should this be? T times t minus 1 over 2 plus 1. The last triangular number, add 1. Right? Yes, that seems to work. Okay, so I claim this is true. And you know what we could do? We could even say, just because I don't want to write the same expression out for evens, so we'll say odd, respectively even. The t odd, respectively even. This is a nice little trick so you don't have to keep writing the same thing over and over again. You say, all right, odd, and then in brackets you say the other case, because it all works out fine. Okay, so we claim that's true for odd t. Now, what about the g's? Well, g's should fill in the remaining gaps. So for an odd t, we should get the even something. What's going on with the g's? So these ones here filled in the gaps here. So, and I claim for even, actually no, it should be, so we'll say odd t's, I'll keep my odd t's. So odd, respectively even t's. Then g something all the way up to g something else are the even. I'm switching the parity because the g's gave me evens when the t that I'm talking about is odd. Are the even respectively odd. What would we say? Numbers in the range. So I want to keep the same t, so t minus 1 squared plus 1 all the way up to t squared. Okay. So that should be fine. I just need to find the right expression in terms of t to make these g's work, and then I will say if true, this proves the result. And you could probably explain a little bit more why this proves the result, but basically take any stretch of numbers in this range, the f's will provide some of them, the g's will provide the others, and that's all you need to do. Yeah, so you could justify that statement a bit more at the end there. But I want to move on to furthering the proof, and I want to figure out what g's I need. So it looks like, so there were t numbers, t such odds, there'll be t minus 1 such t minus 1 numbers filling in the gap that the g's do. So we need to pick, I think we go up to, looks like the previous, this 3 is the t minus first, the second triangular number. And so we'll say t minus 2, t minus 1 all over 2 plus 1. Okay. So that's my claim. I finally have all the expressions worked out. I'm happy with those. So now we just need to go about actually showing this. That's it. And then, as I've said, I sort of claimed that if true, this proves the result. Again, if you want to add to that, that's fine, but I think we're good. Okay, so what do we want to start with? The F's, probably. You could probably say something like, notice F is increasing. That'd be fine, but so we start with tt plus 1 all over 2, wait, tt minus 1. Okay, so we start at the previous triangular number and we add some number. Okay, and we'll say for a between 1 and, what would I need to add to this to get my next triangular number? T. Yeah. So then this is going to be 2, so we can knock off the 2 there. T minus 1 times t plus 2a minus, and because I know how to, so the floor function thing here will have to be t. So I'll have minus t. So I'll get t squared minus t plus 2a. Why is it minus another t? Okay, no, I guess that works. So minus t squared plus 2a. So we'll say t minus 1 squared plus 2a minus 1. So this, we can note, has the same parity as t, which is what we want to have. For odd numbers, we need to get the odd numbers. For even numbers, we need to get the even numbers. But we can also see for a being equal to being in the range 1 to t, we'll get our numbers in the range 2a, so 2, 1 minus 1 would be plus 1. And then if I had 2t minus 1, we'd get t squared. And then we'd be all set. Okay, so that proved the one claim. Now let's prove the other claim. Okay. So g of, now what's our expression? T minus 1, no, t minus 2, t minus 1 all over 2 plus a is going to be t minus 2, t minus 1 plus 2a, and now it'll be plus, and we round up to the nearest one, which is t minus 1. Right? The nearest triangular number is going to be t minus 1, t over 2. And here we're going to have a being between 1 and t minus 1, so this should hopefully work out in essentially the same manner. So adding t minus 1 Here we'll get another t minus 1, so we'll get t minus 2 plus 1, so t minus 1 squared plus 2a. So I notice it has same parity as t minus 1, and therefore opposite parity of t. So if t is odd, these g values are filling in the even numbers, which is what I wanted to show. And then with this particular range of values, what are we going to have? Well, we'll have t minus 1 squared plus 2 all the way to t minus 1 squared plus 2t, which happens to be t squared minus 1, which should work out. And I'm going to say that we're done at that point. I've proved both claims. If it's f and it's the numbers like I said, we get all the odd numbers in this range. If it's g and it's these values, we get all the even numbers in this range. So we can see that we can take certain f's and certain g's to fill in all the numbers between t minus 1 squared plus 1 all the way up to t squared. And we can also see, well, the g's hit evens in that range, and the t's hit odds. There's not going to be any overlap. Again, if you want to add a bit more explanation, if you're unsatisfied with my verbal reasoning here, by all means, add in your own explanation, but I'm happy with it. I think that would be perfectly fine. And there we're done question number 9. So up next is going to be question number 10. We're going to finish off our 2011 Euclid, and I hope to see you there. Until then, take care.